When we talk about climate change, we're usually talking about modern global warming caused by human activity. Earth is more than 4.5 billion years old, and its climate has swung wildly long before humans have ever existed. From hot tub oceans to snowball Earth, with life itself playing a surprisingly large role in how things play out. We'll be tracing the history of Earth's climate as it volleys between sauna and industrial freezer, and then we'll talk about what it says about man-made climate change today. Early Earth was a molten hellscape. Over roughly a billion years, the planet cooled enough for a solid crust, and by about 3.8 billion years ago, the first oceans formed. But it wasn't your blue-skied paradise. Instead, Earth sat under a thick, hazy atmosphere, and the seas were hot, around 70 degrees Celsius or 158 degrees Fahrenheit. The atmosphere was a mix of carbon dioxide, methane, water vapor, nitrogen, and hydrogen sulfide. Carbon dioxide, methane, and water vapor are greenhouse gases, and in high concentrations, they kept the planet toasty, even though the sun was about 30% less bright than it was today. In the depths of these hot tub oceans, the first life formed. Thermophilic, chemotrophic bacteria clustered around hydrothermal vents. Around 3.5 billion years ago, some microbes invented photosynthesis. Early cyanobacteria learned to use sunlight to turn CO2 and water into energy, and they released oxygen as waste. That was catastrophic. Oxygen was toxic to most life at the time, so most chemotrophic bacteria died, as well as most of those early photosynthesizers as well. This was called the Great Oxidation Event, or the GOE, likely one of Earth's earliest mass extinctions. This changed the atmosphere forever. Oxygen destroys methane, a powerful greenhouse gas, cooling the Earth rapidly and sending it hurtling into the Huronian glaciation. When Earth eventually thawed, it was transformed, oxygen-rich, cooler, and dominated by aerobic life. Jump to 716 million years ago. It's a cryogenian period, aka the iconic snowball Earth. Since the Huronian, the climate had been pretty stable. So what caused this deep freeze? The answer lies in the carbon cycle, Earth's climate's thermostat. You see, over millions of years, volcanoes pump a slow but steady stream of carbon dioxide into the atmosphere, keeping the planet warm. At the same time, water erodes rock, creating deposits of mineral ions that bond to dissolve CO2, locking it away in compounds like calcium carbonate. Together, this continuous cycle of volcanoes releasing CO2 and erosion locking it away is what keeps the Earth temperate. The balance was thrown when photosynthesizers entered the stage during the GOE, and was thrown again during the Cryogenian. At the time, the supercontinent Rodinia sat near the equator and was breaking apart. Equatorial regions were warm and wet, which accelerates weathering. The breakup exposed vast amounts of fresh rock, pulling CO2 out of the atmosphere faster than volcanoes could replace it. Temperatures decline and glaciers spread. Ice reflects sunlight, which causes further cooling, leading to more ice. This positive feedback loop, called Runaway's icehouse effect, eventually froze the planet nearly all the way to the equator. Earth escaped only because volcanism never stopped. With continents buried under ice, weathering slowed to a crawl, allowing CO2 to build up in the atmosphere. Still, it took over 50 million years to melt the ice. By the end of the Cryogenian, CO2 levels were extremely high. Rapid warming and intense rainfall followed. Glaciers melted, and erosion flushed massive amounts of calcium, phosphorus, iron, silica, and other nutrients into the oceans. These nutrients helped fuel the Ediacaran and Cambrian explosions, when animal life diversified rapidly, with innovations like shells. I think we've seen more than enough ice. Let's jump to the Permian period. The supercontinent Pangaea supported lush coastal forests and diverse ecosystems, while hardy reptile and mammal ancestors braved the expansive desert at the heart of the continent. Then catastrophe struck. A massive volcanic event erupted in what's now Siberia. For nearly a million years, lava flooded an area larger than Western Europe. But the lava wasn't the main threat. The gases were. You see, these eruptions released staggering amounts of CO2, driving rapid warming. Global temperatures rose by 5 to 10 degrees Celsius. Near the equator, oceans reached 96 degrees Fahrenheit, losing oxygen and forming massive Antarctic dead zones. Warming also released methane from ocean sediments, further amplifying the greenhouse effects and acidifying the seas. On land, toxic gases poisoned ecosystems, and temperatures in the tropics may have exceeded 54 degrees Celsius, or 130 degrees Fahrenheit. This was the Permian-Triassic extinction, the largest mass extinction in Earth's history. About 90% of marine species died out, and extreme conditions persisted for millions of years. Now, we arrive at a world much closer to our own. After the asteroid impact that ended the dinosaurs, the early Cenozoic was already warm, with ice-free poles. Then, 56 million years ago, temperatures spiked during the Paleocene-Eocene thermal maximum, or PETM. We're not quite sure why, but in a span of less than 20,000 years, thousands of gigatons of carbon flooded the atmosphere and oceans. Global temperatures rose by up to 8 degrees Celsius. As in past warming events, methane was released from sediments, oceans acidified, oxygen levels dropped. Eventually, increased weathering drew CO2 back down, but cooling took millions of years. It's worth contrasting this with the Cretaceous, one of the warmest sustained climates of Earth history, with temperatures rivaling the PETM's peak. Despite this similarity, the Cretaceous is known as a period of stability and diversity, while the PETM was a much harsher time. Why? The Cretaceous warmth lasted for tens of millions of years, allowing ecosystems to adapt, as opposed to the PETM's climate shock in a geologic blink of an eye. Into the Quaternary period, Antarctica froze and the planet cooled into a rhythm of ice ages and interglacial periods. Homo sapiens evolved during this fluctuating climate, and all of human recorded civilization arose during the unusually stable warmth of the current interglacial. We've talked about Earth's climate history, but what does this say about modern climate change? Earth's climate has changed before, but rarely at this speed. In the past, major warming events were driven by natural forces like massive volcanic eruptions or shifts in plate tectonics. During the Permian extinction, global temperatures rose 5 to 10 degrees Celsius over tens of thousands of years, and that was enough to wipe out over 90% of marine life. Today, the driver is different. In just 150 years, human activity, primarily the burning of fossil fuels, has increased atmospheric carbon dioxide and warmed the planet by 1.2 degrees Celsius. That rate of warming is at least 10 times faster than most natural warming events in the geological record, including the Great Dying. The warning signs we're seeing today with our instruments and bare eyes are familiar. Rising carbon dioxide, oxygen-poor oceans, acidification, widespread extinction. It's the same old tale unfolding in real time, only it's coming from us. Remember that even single-digit changes in global temperatures matter. A few degrees has the capacity to reshape the planet. Carbon dioxide isn't the villain. It's essential. Without it, Earth would be another ball of ice. But add too much too fast and the system tips. Warming accelerates itself, and cooling back down takes hundreds of thousands of years. The oceans are Earth's first line of defense. They absorb heat, store carbon, and buffer change, but they can be overwhelmed. And when that happens, turning back becomes a whole lot more difficult. And finally, life will find a way. The real question is whether human civilization as we know it will.